All right, final exam tutorial, chapters 5 and 6. Starting with chapter 5, dynamics. A couple of equations that we can use for gravity. The first, Fg equals big G times m1 times m2 all over r squared. Remember in that equation, r is the distance separating the center of the two objects, and just make sure that r is in meters. Fairly common to see that sometimes in centimeters, and that's going to require a conversion. We've also got a shortcut for any object on the surface of the earth, like if a question said, hey, find the weight of a cat. Weight is also known as the force of gravity, and the shortcut Fg equals m times g. Force of gravity pulling down on this cat, where g is just 9.8. We've also got the force of friction, which has to do with the weight pulling down on our cat. Remember, we've got the normal force, which is the force of the ground pushing back up, or any surface pushing back up on an object that's keeping it from sinking into the center of the earth. Usually we will have forces to the right, maybe somebody pushing or somebody pushing. We usually call that just Fa for the applied force. And then if you're pulling or pushing, you've always got that force of friction that's fighting against you, Ff. The force of friction is equal to mu, which is the coefficient of friction, times the normal force. And remember, that normal force is almost always, the only exception is elevators, almost always equal to the force of gravity, m times g. Moving on to spring forces. The force in a spring or a string is, or I should say elastic, Fs equals k times x, where k is your spring constant. It's really just a measurement of how stiff the spring is, and x is your extension. There's another unit you have to watch that needs to be in meters, just in case you see it in centimeters. I will just quickly touch on the one time these can sometimes get a little bit tricky, and that's if you have a hanging mass, like this humanely harnessed cat hanging on the string or spring. Remember that with any kind of hanging mass, you will have gravity pulling down on that mass. And I would ask the question, is the cat sort of falling down towards the earth? And you would probably say no. What's holding the cat up? Well, the spring force is holding the cat up, the spring itself. And if we assume the cat is just dangling there, that means those two forces are exactly balanced. So we could say the spring force is equal to the force of gravity. And if we expand each of those, spring force is equal to kx, gravity is equal to m times g. And that way you can go and solve for any of those variables, probably looking for a k, a spring constant, or an x, an extension in that one. Those questions can all lead us into good old Fnet equals ma. An easy looking equation, but there's tons of info wrapped into that, and lots of different variation. The usual drill for Fnet equals ma is to draw a free body diagram. And remember, in those free body diagrams, we want to include forces only. So we don't want to include things like masses. We don't want to include accelerations. Keep it as just forces. From the free body diagram, like this one up here of the kitty, there's a free body diagram. You'll notice just forces. The usual drill is with that free body diagram, we can use the forces there to figure out Fnet. And remember, Fnet is a bookkeeping item. It's not an actual force. It is the sum of all the real forces. Quite often, and always in Physics 11, you'll find, if we look at this cat example, that one of the directions will cancel out. So for example, we know the force of gravity and the normal force are equal but opposite, so those just cancel each other out, which would mean the net force could be the applied force minus the force of friction. If forces are pointing in the same direction, we add. If forces are opposite each other, then we subtract. So we use F net equals ma. Typically, we're going to solve for the acceleration. And then once we have the acceleration, we would just jump into some kinematics, which would mean doing a VIF-DAT list, and maybe you're solving for a time or a final velocity or something like that. So that's chapter 5, very quick in a nutshell version. Moving into chapter 6, we looked at momentum. Momentum is the symbol P, and the equation for momentum is mass times velocity. Usually we take momentum and we want to know an object's change momentum. So change momentum is delta P. Now the mass typically isn't going to change, but if you have a change momentum, that's because your velocity has changed. And it has some kind of weird units, both momentum and change momentum. Since it's m times v, those units are kilogram meters per second. Very closely related to momentum is impulse. Impulse is F times t. It has units then of Newton seconds. And I said they're closely related. In fact, momentum, change of momentum, and impulse are exactly the same thing. Ft equals m delta v. This equation, having the two sides equal, is kind of nice. That means if you're asked to find change of momentum, you can go with the change of momentum side, or you can cheat and go with the impulse side. If you're asked to find the impulse, you can use F times t, or maybe you're given masses and velocities, you can cheat and use the right-hand side of the equation. Just remember, if you're looking for momentum, stick with the units of kilogram meters per second, regardless of which side you use, and the same for impulse. Stick with units of Newton seconds. We then moved into collisions, which was all about conservation of momentum. And this is always the case. Momentum is conserved. So what we want to talk about then for momentum is what kind of momentum do we have before versus after the collision. So we could have mass number 1 moving with some velocity, and it collides with mass number 2 moving with some velocity. Now sometimes they hit and stick, sometimes they hit and bounce apart. I'll look at the hit and bounce apart version here. So after the collision we have mass number 1 moving with some new final velocity, and mass number 2 moving away with some new final velocity. And since the momentum is conserved before and after, when we go to solve for usually one of the final velocities, we're just going to keep track of all the momentums that were there. So it will look like this. m1 times its initial velocity plus, we then have the momentum of object 2 moving at some initial velocity. That is equal to the momentum of object 1 multiplied by its final velocity plus the momentum of object 2 moving away at its final velocity. And again, the usual drill is to solve for just one of those final velocities. That means you'll know everything else in the equation. Oh, sorry, that was still chapter 6, wasn't it? Now we're into chapter 6, some energy stuff. All right, first one, work. Work is equal to, symbol is W, equal to F times D. The units of work are J for joules. Now remember, key, absolutely key, your force and your distance, they must be parallel. So to calculate work or to do any work, you have to have a force acting over some distance, and they have to be in exactly the same direction. That then takes us into calculations of power. Power, which is a capital P, is equal to work divided by time. So again, that W is work. Time has to be in seconds, and we end up with joule seconds, the units better known as watts. Now, to calculate efficiency, if you need to do that, it's all about having a machine, and we have to ask ourselves, what is this machine doing for us? Now what you'll find in Physics 11 is the energy that goes into the machine. It's always going to be an electric motor, so it's P times T. We do have always with machines some kind of waste. We'll find that the efficiency is always less than 100%, and that waste energy is just some heat. All motors are going to get warm. Then we need to ask ourselves, what kind of useful energy comes out of this machine? And it can be in one of three types. The machine could lift something into the air, which is potential energy. It could make something go fast, which is kinetic energy. Or it could be like the kettle lab that we did, where you're heating something up, mc delta T. Now, the conservation of energy. I'm going to go right into the ultimate version. We have this big equation, mgh plus 1/2 mv squared plus F times D equals mgh plus 1/2 mv squared plus F times D. Now, there were a series of questions we wanted to ask ourselves about all of these terms. The left-hand side is sort of your before side, before some event, and the right-hand side is after. These two sides, the energy is equal because we can't create or destroy energy. We just transform it from one type to another. So you want to ask yourself, does the object start on a hill or in the air? Is the object moving before some event? And is there somebody pushing, sort of helping the object out? So pushing with the object. And we sometimes call that elves. So do we have any elves helping out, maybe pushing the object forward, trying to make it go faster? Now on the after side, we can ask ourselves the same questions. Does the object end up on a hill or in the air? Does the object end up with some velocity, or does it end up moving? And the last one, is there somebody pushing backwards? And I mentioned this quickly in the Chapter 5 section. What force pushes backwards? That's the force of friction. So if you see any friction in there, it's going to be the F times D on the right-hand side. Sometimes we'll call that term heat, because that's what friction creates. Speaking of heat, looking at heat energy by itself, remember that heat energy is mc delta T, where m is your mass in kilograms. C is called the specific heat. It's a number that tells you how hard it is to heat something up. Specific heat. There's a C. I won't even worry about the units in there. Don't sweat that. And then delta T was your change in temperature, and that can be in degrees Celsius or Kelvin. Doesn't matter. And remember, delta T is TF minus TI. Change in anything, final minus initial. We then revisited collisions in this chapter, and we looked at them not necessarily only in terms of momentum, but also in terms of kinetic energy. So what we found for these collisions is kinetic energy may or may not be conserved. We had called those collisions elastic and inelastic, if you remember those terms. And all we're going to do here is something very, very similar to what we did in the collisions up here. But instead of looking at momentum, which is n times v, we're now going to look at kinetic energy. So we've got the kinetic energy of this object before the collision, plus the kinetic energy of object 2 before the collision, and we set those equal to the kinetic energy of the two objects after the collision. And then what you'll usually find is we lose some kinetic energy on the right-hand side. Where does it go? Well, it turns into heat. So usually during collisions things get warm. That's some heat energy, some number of joules. Oh, and I should quickly go back. Remember, anytime you're dealing with collisions, movement to the right is positive. So you'll need to catch that with your velocities. Any movement to the left has to go in as a negative velocity. So there's a quick theory section. Let's apply some of that theory to some questions. So number one, we're looking for the force of attraction between a couple of dump trucks. They're 230 centimeters apart. That is going to be, I'll call it the long equation for the force of gravity. Fg equals big G times m1 times m2 over r squared. Now in this question, big G, remember, is a constant. It's worth 6.67 times 10 to the negative 11. That's on your formula sheet if you need it. The masses of the two dump trucks, 2,500. Ooh, the car and a dump truck, sorry. Times a 16,500 kilogram dump truck. All divided by, let's give you a better one of those. There we go. The distance between them, ooh, bit of an issue on this one. Centimeters apart isn't going to work. Remember, we have to convert into meters, divide by 100. So that's going to be 2.3 meters. And then don't forget, when you plug that number in, we have to square it. Really common mistake is to miss that. And I'll let you go ahead and type all that in your calculator to confirm. But the number you're going to get, 5.2 times 10 to the negative 4. All forces measured in N4 newtons. Moving into number 2, got another force of gravity question here, but things are a little bit different. We've got two masses, but they're unknown. So we're not going to be able to use the equation that we just looked at in number 1. This is a question that's getting at something called the inverse square law. So there's something about that equation we looked at in number 1 that'll let us take a little shortcut here. And that is that r in this equation is in the denominator and it's squared. So I'll show you what this looks like. When we're 64 meters apart, these objects have a force of attraction of 2,400 newtons. We want to know the force of attraction, aka the force of gravity, if we shrink that distance down to 16 meters. So the question becomes, to go from 64 meters down to only 16, how many times closer did we get? Well, 64 divided by 16 is 4 times closer. And we know when objects get closer, the force of gravity is going to increase. Or maybe the easier way to think about it is think about traveling to space. As you get further away from the planet, as r gets bigger, or you get further away, force of gravity shrinks. So here we're getting closer. We know the force of gravity is going to increase. Does that mean that the force of gravity gets 4 times larger? Makes sense, right? 4 times bigger when you're 4 times closer. And the answer is not quite. Remember that the distance between the two objects is squared. That means if we're 4 times closer, we have to square that factor as well. So in this case, we're actually 4 squared times larger for the force of gravity, which would be 16 times larger. Now, if you need to find the actual force of attraction, like this one is asking for, how do we figure out what 16 times bigger than 2,400 newtons is? Well, we're just going to multiply. So we are originally at 2,400 newtons. We want to make this 16 times larger. 38,400 newtons. Now there's 3 sig figs according to a chemist, but maybe a little bit safer to put that in scientific notation. 3.84 times 10 to the 4 newtons. So a cool little shortcut, little trick for that one. Looked like we wouldn't be able to do anything with it, but it worked out just fine. All right, number 3. 12 kilogram meteorite traveling really fast, 300 kilometers an hour, strikes the ground, sinks 40 centimeters into the dirt. Find the average force exerted by the meteorite. So this is going to be an Fnet equals ma question. Now remember, in the theory section I said the usual way to find Fnet was to work with a free body diagram. It turns out in this case probably not the easiest way to do it. We know the mass. That's done. The other thing we can find here is the acceleration. So we've got enough information that we can actually run some kinematics to solve for A, and then we can just multiply m by A to find Fnet. So let's move off to the side here. We'll quickly run some kinematics. We'll make a VifDat list. We do have a couple of issues here. Kilometers per hour, not going to work. Remember, to go from kilometers per hour to meters per second, you divide by 3.6, which I believe gives you an initial velocity of 83.3 meters per second. Final velocity, we can assume this thing sinks into the dirt and stops moving, so that's 0. It sank 40 centimeters. Ugh, another unit to worry about. We need meters. Divide by 100. That's going to give us 0.40 meters. Now we're after the acceleration, so we can plug it into Fnet equals ma. Forgot our stopwatch. And if you go to your formula sheet, you're going to find that this equation works really well. Vf squared equals Vi squared plus 2AD. Plug in all of our numbers here. We're trying to solve for A. There's what it looks like. Remember, we can sort of just multiply over the A there. I'm just going to leave the 83.3 squared for now and just type that into my calculator to make life easy. So that's 0.8 times A. Shuffle that 83.3 squared over to the other side. You get negative 6944 equals 0.8a. The acceleration is negative 8680. 0.6 meters per second squared. Lots of sig figs, but that's okay. We don't want to run into any rounding issues. So now if we steal that number and we go and plug it into Fnet equals ma, 12 kilograms multiplied by that acceleration, you can have it as a positive or a negative. It's not really going to matter. Throw those in your calculator. You're going to get a net force. When you see average, think net. Should mention that as well. You're going to get a net force of 1.04 times 10 to the 5 newtons. Big number, but we slowed that thing down really, really fast. Number 4, find the acceleration of a 10 kilogram crate. We're being pulled with an applied force of 45 newtons, and they give us the coefficient of friction. This is now multiple forces going on. This is your sort of token Fnet equals ma with a free body diagram. So there's our crate. Let's talk about the forces acting on our crate. We've got gravity pulling down, m times g, 10 times 9.8 is 98 newtons. Only going to include forces in this diagram. The crate is not sinking into the center of the earth because the ground is pushing back, the normal force. And that is equal but opposite, 98 newtons. Here we're pulling with 45 newtons. I'm going to call that FA for applied force. And we've got the force of friction fighting backwards. That's equal to mu times the normal force. And we've got both of those. 0.37 times 98. 36.26 newtons. So now that the diagram's done, we want to ask ourselves, what is the net force? So notice that the normal force and the force of gravity, those numbers are going to wipe each other out. We've now got the applied force fighting against the force of friction. And anytime we're fighting with forces, that means we're going to subtract. So the overall force is 45 minus the 36.26 equals 10 times A. And you'll find that when you go to run those numbers, your acceleration 0.874 meters per second squared. Number 5. Running back, colliding. So we've got a collision question here. We do have to watch the direction of the velocities. So east is positive, west has to go in as a negative, and you have to make sure you catch that. We've got the final velocity of the players if they become entangled. Remember, that means the masses are going to combine. So really all you need to know is initial momentum equals final momentum. Got a 72 kilogram running back at 8.5 meters per second plus a 98 kilogram lineman traveling at negative 7.9 equals, now we're going to add those two masses together, 72 plus 98, they wrap each other up, moving away with some final velocity. 612 plus negative 774.2 equals 170 VF. Negative 166.2 equals 170 VF. Final velocity of negative 0.954 meters per second. So there's a collision question where they get stuck together. We saw the one in the theory section where they bounced apart. You've got both the examples you may encounter. Chapter 6, energy. Find the work done when you win a big trophy and you get to walk across the stage. Work is force times distance. So you look at this and you say, okay, the force could be the force of gravity, m times g, 1.8 times 9.8 equals 17.64 newtons. Just trying to hold this trophy up. So there's your force. Can we just take that and multiply by 3.4? And the answer is no. That doesn't work. And the reason for it is that if you are going to calculate work, your force and your distance have to be, the magic word, parallel. And if you're holding up a trophy, that means your forces are up and down. And if you're walking across the stage, D is side to side, that is perpendicular. That is the worst case scenario in terms of completing work. So in this case, nice easy answer, 0 joules. 7, we're going to take our cat for a walk, in air quotes. Wouldn't that be nice if they actually walked? Pulling on a leash with 80 newtons. The leash forms an angle of 30 degrees with the ground. Find the work. There's our cat. Pulling on a leash with 80 newtons. It forms an angle of 30 degrees with the ground. And the cat is moving horizontally, 12 meters. Now, because the cat's moving horizontally 12 meters, when we go to calculate work, F times D, we are stuck with both of them being horizontal. If D is horizontal, then we need to figure out how much F is horizontal. So what we can do is we can turn this into a little triangle. We need to figure out, of that 80 newtons at an angle, how much of it is horizontal. I'm not even going to worry about the vertical section because it doesn't matter. We're into some trig here. It's going to be cosine 30 equals your horizontal force over 80. And you'll find that horizontal force is 69.28 newtons. That's the number we can plug in to calculate work. 69.28 times that horizontal 12 meters. 831 newtons. Let's look at some heat energy. We're looking for some final temperature. We've been heating something, some water with a kettle. Anytime you see heat energy, you know we're going to have to use E equals mc delta T. We've got 650 grams of water, 0.650 kilograms. Specific heat of water, 4180. Remember, delta T is TF minus TI. Or after TF, the initial temperature was 20 degrees. But now we've got this other issue of E, the energy. Remember, watts is actually a measurement of power. But we can get a power into an energy if we're willing to try E equals P times T. So we've got 1200 watts with a time of 2 minutes. More units to worry about. Time needs to be in seconds. So that's going to be 120 seconds, which is 144,000 joules. We steal that number and go and plug it in for E. I'll let you go run the math here. Try and shorten up this video. You will find, once you crunch the numbers, that your final temperature should be 73 degrees. Next one, we got a bunch of stuff going on. A rocket-powered go-kart on a hill, moving, rockets fire. This is a big conservation of energy equation. So I would always treat this as a process of elimination. List all the types of energy that you could have, and then take away the ones that you don't end up with. It's a little bit easier than trying to sort out which ones you do have. So we can ask ourselves, before the bottom of the hill, so there's kind of at the top of the hill compared to the bottom of the hill, there's your before and after. Is this go-kart on a hill? Yes. Is the go-kart moving? Yes. 3.6 meters per second. Is there an elf, somebody pushing? In this case there is. It's the rocket elf. Now, at the bottom of the hill, is this go-kart still in the air / on a hill? No. Is it going to be moving? Yeah, I bet you it's moving fast. And is there any mention of friction, even though it's there? No, there isn't. So now we can go and plug in all the numbers that we've got. 185 was the mass. Oh, sorry. Looking at my notes. Let's put that in there. 185 kilogram rocket. You may recall, since we have this F times D term in here that doesn't include mass, then we can't take masses out. So pardon me not having that number in there. Looked like maybe we could scratch it, but we can't because F times D doesn't have mass. So if you plug all the numbers in, I'll show you all the numbers and go straight to an answer. It's just calculator work once you get all those numbers in there. Do be sure that you square your velocities in the 1/2 mv squared. Again, a really common mistake is for that to sort of just disappear. And when you throw that entire left-hand side into your calculator, 28846.9 equals 92.5 v squared. Run yourself through a few more steps that I'll skip. 17.7 meters per second. So again, treat those conservation of energy questions as an elimination style question. List the whole thing, it takes 10 seconds, and then take out what you don't have. Find the heat produced in question number 5. Oh, question number 5, going all the way back to, sorry. All the way back to this question here, the running back and lineman that collide. So remember, what we're going to do with this one is, instead of talking about conservation of momentum, M's and V's, we're going to talk about conservation of kinetic energies, which is kind of nice because we're just going to change M times V into a 1/2 mv squared. So it looks pretty darn similar. We've just got a couple more numbers to worry about. So we had player 1 before the collision plus player 2 before the collision. They then collide and their masses are going to be combined. And then we want to see if we've got any heat on that side. You may recall that these collision questions where objects stick together, you actually always do end up with heat. That's one thing you do know. So there's going to be some heat there. We need to figure out how many joules. And again, you can flip back. I'm stealing these numbers from that original question. 1/2 times 72 times 8.5 squared plus 1/2 times 98 times, I know it was 7.9 in the negative direction last time, but I'm going to leave it as a positive number here, because if I put it as a negative and I don't remember the brackets when I square it, I'm going to get the wrong answer in the end, and that's something that's really easy to forget. I forget it all the time. So let's just call it a positive, because we know it's going to be positive when we square it anyway. Equals 1/2. The combined mass was 170. We found they moved away at 0.954 meters per second squared. And then we want to find some heat. Looks like the left-hand side is 5659.09 equals 77.36 plus heat. And remember, we're going to solve for heat not by dividing, but just by subtracting that 77.36. You can see there's going to be lots of heat energy here. We end up with an answer of heat equals 5581, which we should put into scientific notation. 5.58 times 10 to the 3. Heat is a type of energy. J for joules. Thanks for watching, folks. If you have any questions, please just bring them on in. Ask Mr. Gower or myself, Mr. Heinrich. Good luck. Happy studying.